MBA633 instructional video prepared by Professor Amit Tata, School of Management, George Mason University. In this segment, we will discuss continuous uniform probability distributions. In the previous segment, we've been introduced to continuous distributions, and we will look at a specific form of it in this one. So consider the following experiment. United Flight 687 flies daily from Los Angeles to Washington Dulles and is scheduled to arrive at 4:48 p.m. The experiment is to record how late the flight is on a given date and in minutes. And let's say we know from historical data that the UA 687 has never been more than 15 minutes early or more than 60 minutes late. Now, if I don't actually have historical data of the pattern of lateness of the flight, I might just, for an initial analysis, assume that the flight is equally likely to be late anywhere between 15 minutes early and 60 minutes late. So all those outcomes between that range, in that range, are equally likely. If that's the case, the probability density function would be as shown over here. It would be a uniform continuous distribution. Why continuous? Because the random variable here, in other words, the time that the flight is late, is continuous, even though I might measure it in minutes and seconds, which may appear discrete at first glance. Time as a physical quantity is continuous, so the random variable is continuous, the lateness of the flight. So x is a continuous variable, and so this is my random variable, is the number of minutes the flight is late. And since all outcomes are equally likely, think of the continuous version of the discrete uniform distribution. If you take a bunch of spikes that are of equal height, an infinite number of them, and stick them together, you will get this rectangle. Okay, so the probability density function in this case is a rectangle. And remember, just as the equivalent of the uniform discrete distribution here, just like the sum of the spikes had to add up to 1, here the area of the rectangle has to be 1, since there are an infinite number of spikes here. So this area under the curve must be equal to 1, and you know that that's true for any continuous distribution. Okay, so let's suppose that you're rushing to the airport to pick up your wife, and you're running late because of a traffic backup, and you want to know what is the probability that the flight will be 15 minutes late or more. So you want the probability that x is greater than or equal to 15. So let's say this is 15. The probability that x is greater than or equal to 15 is simply the area under the curve to the right. So x greater than or equal to 15 is simply the area that I have just shaded. Now, using our knowledge of rectangles, you know the area of a rectangle is simply the base times the height. So this shaded area that I have just drawn is the base, which is 60 minus 15, and that's the base over here, 60 minus 15 times the height. So what is the height of this rectangle? I know that the area of the rectangle is 1. Therefore, its height must be 1 divided by the full base, isn't it? So it's 60 minus 15, because the flight could be 15 minutes early, right? So it's 75 is the base. So the height is 1 divided by 75. So the probability of being 15 minutes late or more is simply 45 divided by 75, whatever that happens to be. So just remember, we are talking about areas under a curve when we are computing probabilities for any continuous distribution. In this case, we are lucky the uniform distribution, continuous one, is a rectangle, so we can use our knowledge of geometry to compute this. Similarly, if you wanted to know what is the likelihood that the flight would be no more than 15 minutes late, you would simply be computing the area on the left over here, and that would give you the probability that the flight would be no more than 15 minutes late. Okay, so if we want to generalize for the continuous uniform distribution. So let's say I have a continuous distribution, probability distribution here, whose lower limit is A and whose upper limit is B. Okay, so if I use the same logic as I did for the United Airlines analysis, the height of the rectangle must be 1 divided by B minus A, correct? Because the area of the rectangle has to be 1. So B minus 1 over B minus A times B minus A, which is the base, would give you an area of 1. Now, the expected value of this random variable is always, since it's a rectangle, the expected value is obviously the middle. So it's A plus B divided by 2. Okay, that's the mean, the average. The expected value is A plus B divided by 2. Now the variance of x, what is the spread or the variability? Remember, that was another metric that we use. You want where's the middle and what's the spread. You can show mathematically, I'm not showing you the proof, but you can show that the variance of x for a continuous random variable, uniform random variable, is B minus A squared divided by 12. Okay, so the difference between the upper limit and the lower limit squared divided by 12. And just like we had for analysis for the United Airlines case, if I want the probability of the value being less than a certain amount x, so here's my value x. If I want the probability of the random variable being less than or equal to x, then that is simply this shaded area that I have drawn. And again, using our knowledge of geometry, this area is simply the base multiplied by the height. So the base is x minus a, which is the numerator, and the height, as we have seen, is b minus a, okay, which is simply 1 over b minus a, I'm sorry, and that's this thing over here. So you can write this as x minus a times 1 over b minus a. Okay, so which is simply the base times the height. So you can use your knowledge of geometry to solve problems of probability involving the continuous uniform distribution. You will not be as fortunate if the distribution is not rectangular or triangular, as you will see soon with the normal distribution. In that case, the logic you will use is the same. In other words, you'll be computing areas under a curve, but you will let Excel do the calculations rather than using a knowledge of geometry. So go just for practice, going back to the United Airlines problem. Suppose I want to find what is the probability that the flight will be between 5 and 15 minutes late. So I want the probability that 5 is less than or equal to x is less than or equal to 15. Okay, so if you think about which I don't want to clutter up this picture with more shadings, but if you think about the logic of it, it will be the area of the rectangle within the limits 5 to 15. Okay, so we're again talking about a shaded area, which is a portion of the distribution function that you see in front of you. So let's see if we can work this logic out without shading anything. It would simply be 15 minus 5, which would be the base of the rectangle were you to shade it, times the height of the rectangle. And you know that the height of the rectangle in this case is 75, isn't it? So the probability that the flight would be between 5 and 15 minutes late is simply 10 divided by 75. So you've seen the arithmetic with the uniform continuous probability distribution, but more importantly, just try to get a handle on the reasoning behind how we compute these probabilities. We are always looking at areas under a curve, and your biggest challenge in solving probability problems with continuous distributions is going from the narrative to identifying which area it is that you want. Once you've done that, the rest of the calculation can be done through Excel or through simple geometry. But the more difficult conceptual part is figuring out which portion of the distribution function you're trying to identify to compute the area. So this is the uniform continuous probability distribution.